This is Lab 2, a follow-up to Lab 1's charged tape as a point charge experiment. My name is David Luton, this is Physics 2212, Group X11, Fall 2020. We'll be exploring one novel principle in this lab, that of the distributed electrostatic charge. That is, charge that's distributed across the surface area of an object, rather than behaving as a singular point charge. We'll be applying some principles from the previous lab as well, like the electric field and electrostatic force, and Newton's second law, which states that an object's force is just a product of its mass and acceleration. As a corollary to this, we'll be looking at gravitational force, or weight. Finally, we're going to be looking at Newton's third law, which states that any exerted force is an equal and opposite reactive force. Now, in both of these examples, as in the previous lab, these are charges, but it would be more accurate to say that they act as distributed charges. There are atomic orbitals around the oxygen, and this cat does have a surface area. An approximately 20 centimeter base strip of clear plastic tape was laid flush across the surface of a table, as shown. Atop this base strip was laid a second, also approximately 20 centimeter test strip of tape. This test strip was quickly pulled off the surface of the base strip, and the resulting transfer of electrons lent a positive charge to the test strip. That is, an electron deficiency existed on the test strip. This was verified by holding it close to a neutral object, my hand in this case. Attraction was observed, and thus a positive charge existed on the tape. This piece of tape was laid across the gap formed by two textbooks, forming a trough, as shown. Now another piece of charged tape was made in the same fashion, and it was also verified to have a positive charge in the same way. This piece of charged tape was slowly lifted from bottom to top towards the trough formed by the charged tape. At the point where levitation was observed, a measurement was taken from the trough minimum to the point that the charged tape was at. A few assumptions were made in this lab, namely, the tape's mass was about 0.20 grams, or about 1 gram per meter, and that the charges on both pieces of tape, the charged strip and the trough strip, were equal. Now, procedurally, there is no difference between this lab and the previous, so the same data was used. Floating was observed at 4.5 centimeters from the trough minimum to the charged piece of tape. Applying Newton's second law, gravitational force is equal to the product of the strip's mass and the acceleration due to gravity. Thus, a weight force of negative 1.96 times 10 to the minus 3 newtons was found. Now, we know that in the y direction, there was no acceleration, since there was no motion in the y direction. It was just static levitation. So we know that the electric force must equally cancel the gravitational force. So it's just the negative of the gravitational force. So an electric force of 1.96 times 10 to the minus 3 newtons was found. These results were then applied to a Glowscript model, where each individual sphere represents a fraction of an overall charge, that is, a dq of an overall q. With this, a tape charge of 1.1612 times 10 to the minus 8 coulombs was found through trial and error. To make this work, a few assumptions were also made. Air resistance played no role, we assumed, and each piece of tape was made up of 10 individual point charges, n. Now, to increase the accuracy of our measurement, we could increase the value of n with diminishing returns with each additional n. We also assumed, as mentioned previously, that the charge of the trough strip and the charge strip were the same. Comparing the computed charges of the rod model and the point model, we see that the point model actually yields a pretty good approximation for the charge of the tape. We're within the same order of magnitude here, 10 to the minus 8 coulombs, and while there is a small difference between the charges, for our purposes it's effectively insignificant. The computed charge in the rod model differs from that of the point model, because in the rod model, each fraction of the overall length of the piece of tape, that is, dl of L, has a slightly different contribution to the net electric field. So the rod model is actually more closely resembling what's happening in real life. This piece of tape has charge distributed across its surface, and we model that distributed charge as any number of point charges, n. And for every increase in n, we're getting closer to what's happening in real life. This concludes my presentation on Lab 2, the rod charge demonstration. Thank you for watching.